So, we were discussing about this mostly the dispersion of pollutants in the atmosphere, and particularly today we will discuss about a very popular model which is used throughout the world, and in very research establishments, many research establishments where this the dispersion models of dust and other things are generally carried out. So, we will see that in this lecture today, and how this distribution or the dispersion model is worked out, and what are its assumptions. As we know that any kind of model should have to have some kind of assumptions. We will also greatly in detail discuss about the assumptions that essentially are linked with a model, air pollution model similar to Gaussian plume distribution here. So, we begin with the mostly there are few important things that we would just begin to discuss with before we actually come to this model. The first and foremost important thing here is the relationship between the height and velocity of air. The relationship between the height and the velocity of air. See here, this is what would be quite important for all of us. See, if you are just trying to understand the situation, mostly all our velocity measurements, air velocity measurements are essentially at the ground level. Say at a height, almost at most of the times at a height within 10 meters from the surface of the earth. So in such cases, it is necessary to sometimes estimate what is the velocity at this height, as at a particular height from the surface. In such a case, we can use this a power function which explains which is explained like this, which is u1 u2 is equal to z1 divided by z2 whole to the power p. Now here u1 and u2, u1 is equal and u1 is equal to u1 and u2, if you can write it like this together, wind speed at higher and lower elevation respectively, and this one is the Z1 and Z2 correspond to a similar height, higher and lower elevation. P, a dimensionless parameter, that varies with stability. That varies with atmospheric stability. So here all you can see is, says mostly in cases u1 by u2. So here it is, say if it is just as for the convention as I have said, u1 and u2, this one is this one is the z1 and this one is z2. Either way, if we know this p and we know u1 and u2 and also another parameter, so z2, in such cases we can find out if this is known to us, if this is known to us, this is known to us, and this is known to us, we can find out what is this. So, by using this power function. Okay. So, the value of this P as the dimensionless parameter I have discussed is essentially depends on another very important factor, which is known as atmospheric stability, So, in such cases, as you can see here, so it's there is the value of P, you can just understand this, there is the value of P. Say P, if we can start a discussion on P, the more stable, remember this, the more stable the atmosphere, remember when we are saying that more stable the atmosphere, we are not saying that there is absolutely no air velocity and there is no such situation, as if not to explain. It should not convey a meaning whereby it states that the wind velocity is 0. It does not mean stability as such. That stability means, there is less turbulence, there would be more of air velocity, can be consistent air velocity. If we can consider that is a stable atmosphere. In an unstable atmosphere, the velocity keeps changing all the time, the velocity keeps changing, and as a result of this, and all velocity, direction, all those things essentially changes in an unstable atmosphere. So, in no way it should convey a meaning that a stable atmosphere means everything is standstill. So, the more stable the atmosphere, the higher the wind speed, becomes, as the elevation increases. And so increases P, and so increases P. So, here also this is so increases P. So, the more stable the atmosphere, the higher the wind speed becomes as the elevation increases, and so increases P. So, you can just consider this P. Also, there is another effect, P is also dependent on the roughness of the terrain. The rougher the terrain, the more the wind speed, near the surface will differ from the wind speed higher up. So, it says this would can see here, just to explain this, the rougher the terrain, the more the wind speed near the surface will differ from the wind speed higher up. So there would be, there is be greater amount of uncertainty, there would be more uncertainty, in calculation, as well as increased value due to the roughness of the terrain. Roughness of the terrain, right? Due to the more uncertainty in calculation, as well as increased value due to the roughness of the terrain, So it's just trying to understand this, so we can estimate, we can have an understanding of the characteristics of P depending on two aspects. One is the stability of the atmosphere and as well as the roughness of the terrain. We will see how actually these values should be used, how these values should be formed. So if it is just to explain it here, why I have come with this expression here, this power function here, is only to suggest one thing, that in many cases in the calculation of the upper velocity at a height, say at few hundred meters, about few hundred meters, if the velocity at the ground level is given, we can estimate the velocity at a higher level. Remember, for this power law function, this power function for this power function holds true for few hundred meters above the ground level, So this is another important thing, is that it can be wherever we are using this, we must use this, that between 0 to say about 300 meters. So this 300 meters is what is we should, more than that, remember, more than that, this power law function does not hold good after say 300 meters, or more or less after 300 meters. So, but at the same time, as it is going up 300 meters, with the calculation of this P becomes increasingly difficult, and also becomes increasingly difficult, and more than that, it should not be applicable. But this will suffice our purpose. You will understand now. This is another important aspect is the atmospheric stability and the value of P. Atmospheric stability and the value of P. I will come back to this atmospheric stability. So, we will further in a generally in a more descriptive manner we will explain this, we will understand the stability. This is what is stability class. I will come back to this. Description and the P and comments. This is A, B, C, D, E, F. This is a stability class. I will come back again, as I have said, to discuss about this A, B, C, D, E, F. Which it means is very unstable, moderately unstable, This can be physically understood as well. I mean, it is not neutral, slightly stable, stable. Slightly stable and stable. Okay. Here what is the value of P is like this: 0.15, 0.15, 0.2, 0.25, 0.40, 0.60, and the common should be in for smooth terrain, smooth terrain, multiply P by 0.6. So, just to interestingly, for smooth terrain multiply by 0.6. See, this is a reducing factor. You can see this. This is a reducing factor for smooth terrain. So, in rough terrain, so smooth terrain and rough terrain, if you do not, if you have a confusion here, yes, a rough terrain would be like this, or more like this is a rough terrain. However, there is a smooth terrain is a relatively smooth surface area. So, if you are estimating the velocity at say at a surface like this and at a surface like this, at these two different surfaces, the value of P would be higher here than the value of P on the smooth terrain. And as you can see, multiplying P by 0.6 is essentially a multiplying by a reducing factor. Okay. So, 0.6 becomes a reducing factor that we have come to know. Okay. Now, here just this is what from next we will try to understand on what basis this the dispersion of this the dispersion of the pollutants take place. We will see we will particularly take this case all these dispersion models. This is in the mostly all this we will consider this smokestack plumes, and adiabatic lapse rate ALR, smokestacks plumes and ALR. See this ALR, I have already said this is adiabatic lapse rate. What we are trying to do now is this we will try to see how this smokestacks plumes, what is a smokestack? See, you have seen, in a power plant, in small plants, small foundry shops, you have found that, you would observe that, there are smokestacks through which the smoke comes out. This is essentially, if we are just not interested about the details at the bottom, you can see this, you have observed the plumes coming out like this. These are called smokestacks. This is where through which the plume generally comes out. So they come out of different shapes. This is come out for different shape. So these are the smokestacks. So this is a smokestack. So they have other names also, you know, so sometimes they would be known as chimneys. Then as in the power plant, you know, they would be known as chimneys. Then they would be simply known as stack. Okay, they would be simply known as stack, etc. So there may be few number of, you know, the nomenclature about the smokestacks. So for all our practical purposes, a smokestack is a relatively tall construction in the form of pipes and chimneys that give out the flue gases in the atmosphere. Though height is important, discharge efficiency may go down, right. Though height is important, discharge efficiency may go down due to the increased height. Though height is important, discharge efficiency may go down due to increased height. So height is important. We will explain, you know, why height is important. Why height is this is called a smokestack, and this adiabatic this is called a smokestack, and we will now observe how, you know, in a different kind of smokestacks, how the plume characteristics changes. Plume's characteristics changes. A plume is an envelope of emitted or discharged gases like CO2, SO2 and SPM formed in the atmospheric column. A plume is an envelope of emitted or discharged gases like CO2, SO2 and SPM, etc. You can think of something else as well, etc. formed in the atmospheric column. A plume is an envelope of emitted / discharged gases like CO2, SO2 and SPM, etc. formed in the atmospheric column. This will come back to this word envelope. I mean, in the course of the lecture. So here, as we further go on to this, as I have said, this is the relationship that we generally observe. See here, the plot that I make here is something like this, you know, where you can see this. Okay. Here what we is that there are two plots here. As you can see this, we would make two plots. Say this is what is adiabatic lapse rate. This is considered this to be, say this considered this to be adiabatic lapse rate. This is would be this is the adiabatic lapse rate curve, ALR. Also, in many books you will find this referred as this with a sign like this, ALR, which it means that adiabatic lapse rate. So what is simple, I mean, if you have not understood it as yet, this is where is the surface temperature. So surface temperature, as I have said, 10 degrees centigrade per kilometer, or say 1 degree centigrade per 100 meter, it will keep on reducing. So if you just plot 2 or 3 line through points on this, from this the surface temperature, and then try to plot it at reducing the value at 100 meters, and then 100 meters, and the reducing the temperature by 1 degree. So you find the plot. So if it is say 25 degrees centigrade here, and another point would be at say 24 degrees centigrade at 100 meter, isn't it? So this should provide you the this adiabatic lapse rate. This adiabatic lapse rate, if you just consider this, with this adiabatic lapse rate, if you just try to find out this the value here, just like this, if it is the atmospheric temperature profile, this is atmospheric temperature which is actually available at the atmospheric, say this is the atmospheric temperature profile, this is the atmospheric temperature profile, which is almost closely resembling to this adiabatic lapse rate in a situation like this. This is adiabatic lapse rate, which is an ideal condition. This is the atmospheric condition. Okay, this is called atmospheric temperature profile. Atmospheric temperature profile. If this is so, we can find the plume model that we can observe here. The plume would show a characteristic like this. The plume would show, irrespective of the height of the stack, it would show a characteristics of the plume would be like this. It would be like this, forming a clearly distributed pattern of, you see this one would be, there would be some changes in this. So but this would be, according to this one, is along the center line, it would be symmetrically distributed along a central line. This is central line. Okay, this is the distributed along the sample line. This particularly would be in a situation like this is known as coning. This is known as coning. Atmospheric temperature profile, is connected with this ALR and atmospheric temperature profile when they are like this in a particular time of the day or in a particular season, when ALR and say atmospheric temperature profile are quite similar or quite close to each other. In such cases, we will find the plume which would be discharged from the smokestack would have an identical distribution on both sides of the central line. Okay, so this is what is called the coning. As in some other cases, we can think of, in cases like this, we can think of a situation like this, where we would find this as this here, that if you just try to plot the same thing, the adiabatic lapse rate does not change. Remember this, adiabatic lapse rate remains same, this one remains same, but if you just observe that this one is being changed to this one is being changed, this atmospheric temperature profile changing like this, atmospheric temperature profile changing like this. We will find this the pollution, particularly the smokestack dispersion of the plume, would be like this. So, we will observe this to be quite similar to this. Okay. So, this is what it would be quite looking like. What is observed here is that what we have generally a more random or a more vigorous, this is along the center line, this should be along the center line. So, you can see this more vigorous up and down movement of the gas plume, This is called as looping. This is called looping. This is how the loops should be formed. This is how the loops should be formed. So, on the other hand, if you just observe this, this is called looping, and on a similar situation like this, if you just observe this one, where it is, where this adiabatic lapse rate remains the same, the adiabatic lapse rate say remaining the same, this one is what is remaining the same. But if we just observe that this particularly the sorry, just 1 minute. I mean, at surface temperature, at the both should be meeting at a one point. I mean, this is, let me cancel this figure. We are just trying to observe this. This is surface temperature in both the cases should be same, isn't it? So, we would start by, if we just make this, somewhere in the middle, say here, this is the adiabatic lapse rate remains the same. This is the adiabatic lapse rate, and if you just observe that this atmospheric temperature profile, the atmospheric temperature profile to be quite like this, you can see a interesting change here is it is decreasing here, it is increasing here. So, the temperature, this, if there are the difference is that this one is the sorry, this one is the ALR that we have shown. This is what is the ATP, that is atmospheric temperature profile. So, we can find here in this case, the pollution, the plume would have a characteristic, which is close to this. What is happening here is this should be in a situation like this. In a situation like this, there would be a relative a sort of compression from both from the up and as well from the below. So, this one is known as fanning. This one is known as fanning. So, here, so whatever the hot gases that would come out of this smokestack, all this, remember, another important thing about the smokestacks plumes is that all these gases are hotter than that of the atmospheric temperature at that point. Remember this. This is also an important parameter or qualification for this smokestack. So, this is how it would be. The fanning would take place, where the zones, this the plume would not be able to be distributed, I mean in a more vigorous way as it has done in the case of coning and looping in the fanning. It would be more or less it would be something like a band instead of a loop, or instead of a cone that you can observe here, this coning that takes place. So this is what is the fanning, coning, looping, fanning that we can see. There is another important changes that we observe here is this one is particularly also quite important, is that this is, as I have already said, this is ALR, as we will find out like this, the ALR as you would say. And here on the other hand, this one is interestingly, see this atmospheric temperature profile here is like this. It is almost following, is quite closely following this adiabatic lapse rate, but then again at a certain altitude it changes course and it goes like this. In such a situation, if we observe here the plume, this the stack at this point of time, at this place, if you see this stack here at this height, what we observe here is that this the plume pattern would be like this. It would be so. As the plume, the surface on the top surface becomes continuously hotter, so there will be the gaseous flue gases that will come out would eventually be denser than the atmospheric at that condition at that point in the atmosphere, at that height in the atmosphere. So if it is forming denser, it will find it to be denser, so it will generally come down. So you can see this, this is what would be the pattern in such case. This pattern is known as fumigation. This pattern is known as fumigation. On the other hand, the last one that we would explain this is also there is another variation to this, another variation with this adiabatic lapse rate and that of adiabatic lapse rate and that of the atmospheric temperature profile. We can observe is if this is the case, and say that you can observe it like this, we can find it like this. Here in such cases we would observe this to be okay. If this is just the other way around, you can see this, whereas here it was, if you just see from the former, this one is, it has actually, I mean if I just change this plot here, it has actually, on the other hand, here the temperature profile is like this, here it has changed like this. Till this time it contradicts, or it is completely different than the adiabatic lapse rate. It is an increasing curve, and on the other hand, as it comes to a stack height, it is essentially changing, and where it begins to follow the adiabatic lapse rate, right. This is what is the plot I have made. You see this, it goes against the adiabatic lapse rate till at the smokestack height, and then from that height onward it begins to follow the adiabatic lapse rate again. It begins to come closer to the adiabatic lapse rate. In such cases, we observe that the particularly the smokestack pollution, the smokestack emission would form a plume which would be like this. It would be like this, since it would be since it would be just the other way around, it would form, it will find lighter. Here it was denser, which was being discharged from the atmospheric air. Here it is lighter than the atmospheric air present at that point of time, present at that place. So here it would be rising. So it is generally called as lofting. It's known as lofting. It's known as lofting. Okay. Now, having to say this, these are the typical characteristics that we observe in cases like, you know, the dispersion of this air pollutants across, you know, from emanating from a smokestack, emanating from a say the power plant discharges that you observe. Next time when you take a travel, you know, wherever you find a power plant, you start to observe, you know, how these plumes actually behave. What you will find some interesting observations in that. In many of these cases, you will find these patterns are being followed. These patterns are being followed. So what we begin to say from this now onwards is that, you know, as we can find out, we have found out that, you know, the different profiles that it would have. See, the mostly this coning, looping, fanning, fumigation and lofting. So having to understood from here that we can go into this the Gaussian plume distribution model, which goes like this. This particularly, you know, beginning to understand this, you know, it would require a certain amount of drawing here. Just, you know, as you can see, this would be okay. Let me draw it from here. This is what is a smokestack. This Gaussian plume distribution is basically following the normal distribution. This is basically following the normal distribution, and how it looks like. This is what it would look like. So here in this case is, as we can observe, okay, this would be the plume. This would be the plume, right? This is what is the plume. See this, you know, this, as you can observe here, if you just try to observe this like this, you know, it would be, say, initially, if you just make a cross section, like this, this would be forming like this initially, then it would be forming like this, then it is, as with the distance, the plume is taking a shape like this. This is what is the plume would look like this physically with distance, starting from this place here. If you just try to observe the plume, you know, facing the plume, if you just try to observe, say here, it would begin to disperse, the pollutants would begin to disperse like this. The pollutants would begin to disperse like this. So here, as you can see, that the concentration here would be higher concentration, it would go to lower concentration, higher to lower concentration, but it would spread like this. This is the spread. This is what is known as the plume. If you make a cross section along this, it would look like this, or quite look like this. So here you can see this, you know, there's one important thing here is, you know, every plume generally for the Gaussian plume we would understand that this should be forming a center line. It's not necessary that all plumes should follow center line, but we would observe for this Gaussian plume distribution to have a center line, and this would be I'll come back to this. This would be forming a symmetrical distribution on both sides. So you can see these are these two end, these two sides are these two sides and these two sides. These two sides, this one and this would be identical. This would be quite identical. So, you know what Gaussian, this is the Plume boundary. So, this is known as this time averaged Plume envelope. Time averaged Plume envelope. Time averaged plume, but instantaneous plume would be like this. Instantaneous plume would not be quite like this. The instantaneous plume would be instantaneous plume would be quite like this. It would begin to spread, but it would remain confined within the plume. So, this is called instantaneous plume boundary. It's known as instantaneous plume boundary. This is time averaged, this is time averaged plume center line. Time averaged plume center line, and this one we would require this explanation. This is the H, is the stack height. This is the above the center line, this about this position here. This one would be known as del H, H and del H. So, this one is del H, that is the lift. As they are, you know, there is a very hot gases, as I have said, all of these are hot gases, they will have sudden buoyancy in them, essentially, isn't it? So, the surface temperature, the temperature of this emitted gases or this particulates would be more than the ambient temperature at that point. So, as a result of this, this would form a certain kind of buoyancy on that. This buoyancy would take them a lift, buoyancy would allow them to get lifted. So, this buoyancy, you know, here as though we have written this del H to be as if to suggest, you know, del H is very small compared to H. It is not so. In most of the practical cases, you know, we would see, we find, say, the del H to be about 60% of H, 60% of H, and this the range is about 60% to, in sometimes it can be up to 120% of H. So, it can be sometimes even more. It can be sometimes even more. It can be sometimes even more. So, you know, you can see this more than the H, you can see this. So, though we have said this to be like this, so, you know, mostly it would be somewhat, you know, the value is quite substantial. It is not like a del H that we generally know of. See, this del H, for most of the cases, you can find, if you are working out in the examination or any other places, you can generally estimate this H, del H to be, if it is nothing else is given, about del H should be about 75%, 70% of H. So, which would makes it is a quite a big value by all means, quite a big value by all means. You can see this one would be, this would be the height is the z axis that we will come back to talk about. This is what is the x, this is the along this line, along a distance at the point where we would measure this, point where we would try to understand the concentration. This one is this distance, the distance would be known as x. This is the x from the point here, okay, and this one is known as, this is what is the instantaneous, this is the plume envelope. This plume envelope under Gaussian plume dispersion model will have certain assumptions. We will talk about that in the next class. Okay, right. Right. So we begin this, again, the Gaussian plume distribution that we are discussing of. See, there are a few interesting things to observe here. What we essentially discuss about this Gaussian plume. See, if you see this plume here, just suppose you are taking a cross section of the plume. At any point, you are taking a cross section of the plume. You see cross section of the plume along its line of travel. So this is traveling, say, the plume as we have already discussed about the plume taking a shape like this, Let me consider that we are taking an imaginary cross section inside this. So what we observe here is, what is under this Gaussian plume distribution is, one thing that it says is that across this, see here, this particularly at this point, if you just observe in this projection here, if you just make a projection here, it would be, it says the distribution is completely normal. That means it would be having a mean, and it would have a standard deviation, and this is across the center line. So this is, say, this is along the center line, this is mu, this is this, this is 2, or say whatever, say just say 3 sigma, this is 3 sigma here, this is what is 1, this is, say, across, see, if we can say this is sigma z, this is sigma z, this is one thing. But there would be across, this is one part, there would be another along this also, this would be following, so another normal distribution. It would be always a normal distribution, which is the center line, from the center line, say this, from the center line, from the mu again on the center line concentration at that point of time. This would be here, this is again a sigma x, sigma x, this is sigma z we have written in the first place, this is sigma x, and also along, if you can just observe this, also along the same, also along this, the y direction, also along the y direction, it would also have a normal distribution, which is again, as you can see, we will have a mu, the mu as we know of, and then this is sigma y. This is across the center line, this is about the center line, this. So this is where it is, the center line is, the center line. So this is, so what it's observed is across x, y, z direction. So mostly the power plant, the discharges would be in terms of tons per day. A power plant, usual power plants essentially emits to the tune of 20 to 50 tons of, say, tons of sulfur dioxide, right, the tons of particulates. So in such cases we have to concentrate, change it to microgram per meter cube. Remember this, don't ever confuse this. X is equal to the distance directly downwind, directly downwind, this is m, distance directly downwind, directly downwind, this is y, downwind along center line, you can write this along center line, this is important. The line of x should be set on the center line itself. Say this is y is the horizontal distance from plume center line. Horizontal, that is from the line of x, the line from x in meter. This is all in meter. Remember this is of great importance. This is a meter. I will tell you why this is of great importance, because most of this sigma x values, sigma z and sigma y values would be given in terms of meters. Q is emission rate. Emission rate of pollutants. Emission rate of pollutants. Here emission rate of pollutants more than what I said is microgram per second. Say that this is I made a mistake here. Clue is second here. You can see, just make a correction. Tons per day can be only be converted into microgram per second. It cannot be microgram per meter cube. I am sorry. This was emission rate of the pollutants. Essentially, this one would be, this particular thing would be required here. This would be given in tons per day, and you have to convert it into microgram per second. Just this one is superfluous. This is not much of importance, because this one is important, where this value would be essentially be changed by all these parameters. Okay. So here this is ton per day. If it is given a power plant emitting pollutants at tons per day, it has to be changed into microgram per second. H, as I have said, H is the effective stack height.